Dr. Wendi Liu obtained his PhD from University of Strathclyde. He's a senior computational scientist at Dasbury Laboratory, STFC, and his research interests include novel approaches to the simulation of fluid structure interactions, numerical simulation of thermoelastic problems, and relevantly, multiphysics code coupling within high performance computing. And now over to you.
Okay, thank you very much. I think you can hear me well and see my slides.
Yep.
As introduced by Shuisheng, my name is Wendi Liu, and I'm working at the Computational Engineering and Environment Group at the Science and Technology Facilities Council. And in this talk, I'm going to give an overview of our recent published results on the conjugate heat transfer and wall thermal strength of the U band by using the code coupling approach. Before the details of the study, I would give a quick introduction on our Computational Engineering and Environment Group. Our group focuses especially on the high performance computing capability to model a range of fluid flows with different applications. And the nuclear reactor and the low carbon energy is one of the strategic themes of our group. We have 7 group members working on this theme and led by our group leader, Professor David Emerson. The research and development activities under this theme includes the general thermal hydraulics, the CFD simulation of different types of nuclear reactors, the thermal fluid structure interaction, and other relevant multiscale and multiphysics simulations. And the study I'm going to present today is the thermal fluid structure interaction of a U-band cooling pipe in a PWR nuclear power plant. Well, the U-shaped configuration is commonly used as the cooling pipe of the nuclear power plant. And in some situations, it will withstand multiple cycles of the hot and cold thermal fluids with a large temperature difference. Since the thermal transient will bring a high risk to the U-band and may cause the strength corrosion or cracking in service, which will cause hazard in reality. So the predicting of the thermal strength is a key element in the design of the U-band. Simulating pipe thermal strength is challenging due to the coupled nature of the governing equations. In compare with the straight pipes, the heat transfer of a U-band has some unique phenomenon, such as the secondary flows during its band, which will make the thermal strength simulation more challenging. And in this study, we will use coupled code to investigate the influence of the thermal transient to the thermal strength and fatigue life of the U-band pipe. More specifically, we will apply several hot and cold thermal fluids with different of the temperature difference and see how the thermal strength and fatigue life of the U-band pipe will respond. Due to the nature of the research question, we need to use a multiphysics simulation code for this study, which is able to simulate the conjugate heat transfer between the solid U-band structure and the thermal fluid inside. And also, we need to simulate the thermal deformation, the thermal strength to predict the fatigue life of the U-band wall. Therefore, we established a framework with 3 simulation domains across 2 codes, as shown in this slide. On the left-hand side, we have the finite volume fluid domain for the simulation of the fluid flow inside the U-band pipe, and also the finite volume structure domain for the simulation of the heat transfer of the U-band wall as modeled by using Coulter version 5.0 by itself, the modeling of the conjugate heat transfer is achieved by the internal coupling between the finite volume fluid and finite volume structure domains by using the consistent of temperature and heat flux between the domains, and employed the PLE library inside Coulter for this kind of coupling. The partial T divided by partial N in the equation is the derivative along the vector normal to the fluid-solid interface, and the kappa is the thermal conductivity. The fluid flow is governed by the incompressible Rans equation. The turbulence closure is achieved through the use of the EBRSM turbulence model. The turbulent heat flux are modeled by the GGDH approach, and the buoyancy is accounted for in both the gravitational source term and the turbulence production for the fluid simulations. And on the right-hand side, we have the Phoenix version 2019.1.0 for the finite element structure domain for the simulation of the thermal-induced strengths of the U-band wall. Linear thermoelastic formulations are implemented, and the finite element solver also implement the empirical equation to predict the fatigue life of the U-band, followed by the past publications. As in this study, the thermal displacement have very less contribution to the simulation of the fluid domain. So one-way coupling, one-way data passing approach is used for this framework between the finite volume structure domain and finite element structure domain. The temperature distribution of the U-band wall, which is obtained from the finite volume structure domain of the conjugate heat transfer simulation, is passed to the finite element structure solver through the file I/O. In order to ensure the consistent interpolation of the temperature distribution between the non-conformal finite volume and finite element structure meshes, the Lagrangian polynomial interpolation is used. And the U-band has a diameter of D for its pipe, and the wall thickness is 0.05 D. The length of both vertical sections is 10 D, while the radius of the curvature of the both of the bands is 1.5 D. The near horizontal section is 6 D long with a small slope. We applied the gravitational acceleration towards the negative y-axis direction, and the U-band has 2 point-based displacement constraints at the inlet and outlet boundaries, as shown as the red dot in the figure. The flow, thermal, and material properties of the study are determined from the dimensionless group shown in this slide. The ratio of the thermal diffusivity and thermal conductivities are based on the water flowing within the steel pipe. The fluid numbers is a key parameter for this study. We have adopted 3 fluid numbers to investigate how of the influence changing the fluid region has on the thermal strengths. The change of the fluid number are achieved by varying the delta T, which is the temperature difference between the initial temperature of the pipe and the thermal transient. The flow is fully developed at the inlet. A hot shock is introduced from the inlet at the non-dimensional time equals to 0, and it's increased linearly until the time equals to 7.5. And it will continue to remain the maximum temperature after time equals to 7.5. After the mesh sensitivity test, we employed 4 million cells for the finite volume fluid domain, 500,000 cells for the finite volume solid domain, and 500,000 tetrahedron elements in the finite element solid domain. The RANS conjugate heat transfer results have been validated against the ensemble LES RANS as shown on the plot. It's agreed well between each other. The finite element solver on the modeling of the thermal deformation and the thermal strength is also validated against both the 2D and 3D widely adopted benchmark cases. And both of these cases has shown good agreement between the present results and the published results. After a series of simulations by the framework, we obtained the results in all domains. First, we focus on the thermal flow and the conjugate heat transfer between the finite volume fluid domain and the finite volume solid domain. We observed a strong stratification in the thermal fluid with a large buoyancy-induced recirculation region around the downstream band, as shown on the figure at the top. We then take a slice at the near horizontal section of the pipe to further investigate the fluid flow as in the bottom figure. And we observed that the dense vortices have been surprised and a counter-rotating vortex pair is formed. This is due to the buoyancy effect between the cold, dense near-wall fluid and hot, light fluid at the core of the pipe. We also plotted the flattened wall temperature contour over the time to show how the U-band wall is heated by the thermal transient. The vertical axis of this flattened contour is the angle of the pipe along the cross-section, and the horizontal axis is the longitude direction along the U-band. The two regions enclosed by the dashed line are the locations of the bands of the U-shaped pipe. The temperature is normalized by the temperature difference between the cold pipe and the hot fluids. We can observe a thermal lag of the U-band wall due to the thermal inertia. At T equals to 15, the thermal front has already traveled to the near horizontal section. But as we can see from the very top figure, the upstream vertical section is still far below the temperature of the thermal transient. As the time increases, both the upstream and the downstream vertical sections are gradually being heated by the thermal fluid. However, both of these sections have not been fully reached to the temperature of the thermal fluid until T equals to 60, as we can see from the very bottom figure. A cold region at the bottom of the near horizontal section can be observed, which is due to the stratification of the thermal fluid caused by the combination of the secondary flow and the recirculation, as we have already seen from my last slide. The Froude number is a key condition to quantify the significance of the buoyancy effect over the flow inertia. As we vary the Froude number by changing the temperature of the thermal fluid with increasing the Froude number, the temperature difference between the cold dense near wall fluid and the hot light fluid at the core of the pipe will reduce. And the significance of the buoyancy effect will reduce as well. And this will lead to a decrease of the strength of the secondary flow and a small of the recirculation region. And the stratification will be weaker in the fluid domain. And this phenomenon is reflected in the wall temperature as in this slide. For small Froude numbers at the top plot, the cold region has a larger area and a steep temperature gradient with its surrounding, while the opposite is observed for large Froude number from the bottom plot. And now we move on to the finite element solid domain to investigate how the stratification and the secondary flow of the thermal transient affect the deformation and the strength of the pipe structure. Since the temperature of the U-band wall is much higher than the room temperature with a large temperature variation, so the Young's modulus and thermal conductivity are treated as functions of temperature in the present study. The contours of the thermal-induced deformation with its magnitude and components are plotted. The junctions of the band at the near horizontal section have the largest deformation according to the deformation magnitude contour at the very top. And the maximum x-axis deformation is in the two bands with opposite directions, while the maximum y-axis deformation is in the near horizontal section. And we also plotted the maximum thermal deformation magnitude with different Froude number, which shows a decrease of the maximum deformation magnitude with a large Froude number. This variation is the contribution from both the stratification-induced temperature gradient and the difference of the temperature difference between the cold pipe and the hot thermal fluid. Well, the thermal strength is believed to be a combination of the effect from three sources. They are the shape of the geometry, such as the bands or junctions, and also the temperature gradient of the U-band wall. And the last source will be the temperature difference for different Froude number. There is a positive correlation between the pipe temperature gradient and the thermal strength. The Van Mises strength contour for different Froude number are plotted in this slide. And we can see there are two types of area subject to a very large thermal strength. One is the front and back part of the two bands, and the other is the bottom of the horizontal section. With the increase in the Froude number, the thermal strength decrease in these high strength regions. And it is again due to the decrease of the stratification-induced temperature gradient and also the decrease of the temperature difference in different Froude number. And we further analysis the fatigue life of the U-band. We made several assumptions in the fatigue life prediction, such as to assume there's no denting presented in the structure. And we also assume that the hot and cold water injection cycles are symmetrical. With the present working condition and assumptions, the contours of the cycles to failure with different Froude numbers are plotted in this slide. And as we can see, the patterns of the fatigue contour is quite close to that of the stress contour, as we can see from my last slide. A small Froude number has a large thermal strength, which leads to a short fatigue life. And in all of these Froude numbers, the weakest part of the U-band is at the front and back part of the two bands. And these are part of the results from our recent publication on the thermal fluid structure interaction of the U-band by using Coupl codes. If you are interested in that, please feel free to read our papers. And before I finish, I would like to update the recent development on the multiphysics simulation code since this study. This flowchart shows the latest version of our multiphysics simulation framework. On the left-hand side, we have the finite volume fluid domain, which using the OpenFOAM version 6. Both the single phase and multi-phase fluid solver have been implemented. And on the right-hand side, the finite element structure domain, which remains the Phoenix version 2019.1.0, both the generalized harmonic oscillator model and the hyperelastic model have been implemented in Phoenix for the simulation of both the small structure deformation and the large hyperelastic deformations. And we employed an interface coupling tool for the communication and the data sharing which is the multiscale universal interface MUI version 1.0. And it enables the fully two-way coupling between couples, and it also have a very good scalability, which suits the parallel simulation with massive meshes. The codes implemented in the latest framework are all open source codes, and the entire framework is also available to the public in GitHub. It has been validated for each component and also for the entire framework and uses in other applications. It can also apply to the simulations on the thermal fluid structure interactions in terms of the nuclear thermal hydraulics field, such as the damage of the tube bundles due to the thermal flow induced vibrations in the nuclear reactors and so on. This framework is under active development and at the moment, ongoing work to further enhance the parallel performance of the framework towards the X-scale simulation is currently underway, which funded by the Archer 2 ECSE program. It includes to implement the latest code Saturn as the finite volume CFD solver on the left-hand side of the flow chart to take the advantages of its good parallel efficiency, and also identify and fix the bottleneck of the framework by code profiling. So that's all from me. Thanks for listening. I'm happy to answer your questions.
Right. Thank you, Wendi, again. And that was interesting talk and well time as well. So yeah, we have time for a couple of questions, if there are any. And actually, can I make a start just on this last slide and the one before this, please? And for the coupling, I'm just wondering whether the things that you said is open source, and I'm just wondering whether it's kind of flexible for different code coupling. You currently have open form. You say you're going to develop our Coupl, the co-Saturn as well. I'm just wondering whether ultimately you're trying to make it like a generic coupling too, or what's the ultimate goal of this?
We would like to have a kind of multi-physical coupling tool which is able to tackle different types of multi-physical simulations. Currently, there are several libraries can achieve that by using a similar partition or monolithic approach. But what we want is something quite flexible so that we can implement some or to apply it to a new case very easily. And we also would like to have a kind of framework with high scalability so that we can simulate some large simulations like the nuclear reactors when the thermal fluid and structure is involved, and we require to build up a very complex geometry inside that. And we also want the framework is extendable so that we can involve as many physical domains as we want. And by reviewing the existing libraries, we find out that it is better for us to build up a kind of framework according to our needs. That is the start of this story. And as I presented during the presentation, at the very beginning, we use Code Saturn and Phoenix, and use a one-way data sharing approach to carry out the very simple case to proof of the concept. And then we implement the by using the interfacing library to enhance its ability, including to enhance its scalability and flexibility and extendability. But
yeah, sorry, yeah.
But each library have its own advantages and disadvantages. The open form have so many functions inside that, but if we go very large simulations, open form may not as good as the scalability. And the code Saturn is very good at its scalability. So that's why at this stage, we would like to implement the code Saturn as the CFD part to further enhance its scalability of the whole framework.
All right, thank you. We still have a couple of minutes for any quick question, if there are any.
Maybe I have one. So thanks for your presentation. I was wondering if you had, in the U-bend case, did you consider the possibility of moving the Saturn mesh to fit with the Phoenix deformation?
Currently, no. As I shown in my very beginning, only one-way data sharing is considered in the present study, because by evaluating the current working conditions of this case, the deformation of the U-band is quite limited, and we just ignored the U-band expansion to the fluid flow. And in this case, only the thermal fluid have influence to the strength and the deformation, but the deformation will not feed back to the thermal flow. Maybe in the future, we can, by using the latest version of the framework, we can have the fully two-way coupling for this simulation to further enhance its accuracy.
Thank you.
All right, thank you very much. We should move on to the next talk, and then at the end, gives you have opportunity to ask questions.